Today we're going to talk about exponential decay, which is very, very similar to exponential growth. We're going to see one change in the graph of these functions as opposed to what we saw in the previous lesson. So an exponential decay graph looks like this. So we looked at exponential growth in the previous lessons, and exponential growth could look like this or like this. So the difference about an exponential decay and an exponential growth is for growth, as we read across our paper, like you read across a book from left to right, in a growth, the graph is moving away from flat. And a decay, the graph is moving towards being flat. Okay. The equations are going to look pretty much the same. We're going to graph them again with XY charts. When you plug in a -1, it's going to flip over that fraction. So you get 15 halves or 7.5. Plug in 0, and it gives us the coefficient and the number in the front. Plug in 1, and I would have 5 times 2/3, which is 10/3 or 3 1/3. Plug in 2, and it'll square that fraction. So I get 20/9, or 2 2/9. And plot these out. -1, 7.5. 0, 5. 1, 3 1/3. 2, 2 2/9. And we can see that the graph then is starting high and taking its turn to flatten out. They're still going to have arrows on both ends. They still have a horizontal asymptote. The difference between a growth and a decay is that a growth is moving away from its asymptote and the decay is moving towards its asymptote. Otherwise, this lesson is very much the same as what we looked at in lesson 1. So what do you think is different about the equation that makes this a decay as opposed to a growth? So, I mean, because it looks really like exactly the same equation. So how could we look at this equation and see a difference in it to be able to tell whether we're going to have a growth or a decay?
It's a fraction.
The base is a fraction, and it's a fraction smaller than 1. So even if it were some kind of a fraction like 3 halves, that's larger than 1, we would still have a growth. But when that base is a fraction smaller than 1, we'll have a decay function. So in this one, is it going to be a decay or a growth?
Okay.
This is actually going to be a growth function because that base is larger than 1. The base is 3 halves or 1.5. So this is actually going to be a growth function, and it will be exactly like we did in lesson 1. So we're going to plug in the -1. It's going to flip over that fraction, make it 2/3. Get -16/3. -8. -8 times 3 halves is -12, and I'm not even going to bother plugging in that last one because I know whatever it is, I'm not going to end up plotting it because it's going to be too low. So -1, 16/3 is 5 1/3. And I've got a -8. And I can't even really get the -12. It's going to be all the way down here somewhere. So this is a growth function. It's a negative growth function, but it's a growth function because as we move across the paper, it's moving away from being flat. It's moving away from its asymptote. So when our base is smaller than 1, we're going to have a decay. When our base is larger than 1, we will have a growth.
Why didn't you do the 2?
Because there was no way I was going to be able to fit it on my graph.
Oh, okay.
So I could just tell by where the numbers were going that it wasn't even worth figuring it out.
Wait, larger than 1. Okay.
Larger than 1 is growth. Smaller than 1 is decay. So this is a growth function. It's growth because it's moving away from the asymptote. So it's negative growth, but it's still growth. This one has something different show up in it in that our exponent is a negative number. So let's see what that does to our graph. You have to be careful plugging things in then because we're going to have 10 times 3 to the negative 1. Since the equation already has a negative, and now I'm plugging in a negative 1 for x. So negative 1 is really positive 1. This 10 times 3 or 30. Probably not going to plot that. Anytime you plug in 0, you're just going to get the front number. And when I plug in 1, I'm going to have 10 times 3 to the negative 1 because the equation has a negative in there, and our x is 1. So that negative 1 exponent is going to flip it over, and this becomes 10 thirds or 3 1/3. When I plug in a 2, the equation will make it negative because there was a negative in front of the x in the equation. So this is going to flip and square that 3. Flip because it's negative, square because the 2's there. So this gives us 10/9 or 1.1. So 10 is already somewhere up here. So I'm not going to plot the 30. 3 1/3, 1.1. So is this decay or growth? Decay. So there are two ways that decay can occur. Decay can occur when your base is a fraction smaller than 1, or if your base is larger than 1 but you have a negative exponent. Okay, so because of that negative up with the x, that creates the decay. So either a base as a fraction smaller than 1, or if the base is larger than 1 but we have a negative exponent, that will create a decay graph. So this one's going to be a decay graph because that base is a fraction smaller than 1. We have some shifting that happens in this graph though. What does the plus 2 do to the graph? Left. And what's the plus 1 do? Up 1. So we're going to start by moving our graph to the left 2 and up 1. Then we're going to work just with the non-shifted part of the function to create our chart. When I plug in a negative 1, it's going to flip over that fraction to make it 2. So I get negative 6. Plug in 0, I get the front number. Plug in 1, I get negative 3 times a half, or negative 1.5. Plug in 2, I'm going to get negative 3 times a half squared, which is a fourth, or negative 0.75. You can use your base to tell what should be happening in your chart. Your base is what we're multiplying by each time, because that's what a power does. It means that we're multiplying by that same thing over and over and over. That's what a power is really doing. So with a base of a half, that means I should be multiplying by a half each step along the way. So we found our first answer was negative 6. Then we should be multiplying by a half each step of the way. So half of that is negative 3, half of that is negative 1.5, half of that is negative 0.75. So we can use that base to figure out what should be happening in our chart. With a base of 1/2, we should be multiplying by 1/2 each time. So we're going to plot these points, and since there was shifting and we plugged it into the altered equation and not the original equation, we're going to plug it into our altered or shifted axes. So pretending like where those red lines meet is the origin, I'm going to go back 1 and down 6. over 0 and down 3, over 1 and down 1.5, over 2 and down 3/4. And we do get a decay equation because it's a flattening. It's a negative decay equation because it's on the bottom half, but it is still decay because it has that flattening as we move across towards the right. Domain and range. Domain, just like for growth, will be all real. So we can plug anything we want in for x. Range, just like for growth, is limited by the asymptote. So we're going to have y. Is it going to be greater or less? Less because it's on the bottom half of the graph. And what is it less than? What line bounds it off? 1. Okay. The asymptote is going to bound it off, so it's never going to actually touch that line or cross it. So we have just less than 1. First thing we'll do is take care of the shifting. So what's the plus 1 going to do? Left 1 and minus 2? Down 2. Then we're going to work just with the altered equation, ignoring the shifting. When I plug in -1, it's going to flip over that 1/8 to make it 8. I'm going to get 40. I'm probably not going to plot that unless I would want to start scaling by something else. If I plug in 0, I get the front number, which is 5. Plug in 5, and I have 5 times 1/8. 5/8, which is a little bit more than a half. Plug in 2, and I'm going to have 5 times 1/8 squared, or 1/64. So get 5/64, which is very, very tiny. So in our chart with just these 4 values, we go from very big to very small. Okay? We said with a growth, the larger that base is, the sharper the turn we're going to see. Same thing with decay, but we're thinking about the closer that base is to 0, the sharper of a turn we're going to see. So a base of 1/2, we're going to see kind of a moderate turn to it. But as that base becomes closer and closer to 0, we're going to see a really sharp turn happen in our graph. So I'm not going to plot the 40. I will plot the 0, 5. And we plot it from our shifted axes since we're using our altered equation here. So 1, 2, 3, 4, 5 there. 5/8 is just a little bit more than a half. And then 5/64, I don't even think I can plot that because it's so close to 0. So we see a really sharp turn happen in this graph. Okay, with a growth, the bigger that base is, the more sharp of a turn we're going to see. And with a decay, the closer it is to 0, the sharper of a turn we're going to see. Or as a general rule, the further away it is from 1, the sharper of a turn we're going to see. Domain and range. Domain is all reals. Range is our y values. Is it going to be greater or less? Greater and greater than what? -2. That asymptote line at -2 is cutting off the graph, so we're never going to get anything below that. For applications, our equation here looks almost exactly the same as the equation yesterday, but when we were working with growth, we had a plus in there. We did 1 plus our rate, because that gave us a rate then, or a base, of bigger than 1. So bigger than 1 causes a growth. If we're taking our rate and subtracting it from 1, this is going to give us a base smaller than 1, which will create a decay. So the equation is almost exactly the same, except for when we add, we get larger than 1, so we get growth. When we subtract, we get smaller than 1, which will give us decay. You buy a new car for $24,000. The value of the car decreases by 16% each year. That's actually kind of a moderate assumption. I think most cars decrease more quickly than that. So we're going to use A1 minus R to the T since we're decreasing our value here. We're going to use our subtraction or our decay. Just like yesterday, the A value is the initial value of the car. R is our interest rate as a decimal, so 0.16 to the power of T. For a model, you should have two variables in your equation. A model is an equation that shows how two different things are related to each other. So you need two letters in there to show that relationship. So make sure when it tells you to write a model that you're just writing the equation, not plugging in anything for your variables. Then it says use that model now to estimate the value of the car after 2 years. So now we're going to plug a 2 into this equation. Need a calculator on this. Let me just plug it in and feel free to round it off. So I get 16,934. So after 2 years, my car is worth a little bit less than $17,000.
Why did the number in the parentheses change from? Oh, never mind.
The second part wants us to graph this, and then the third part wants us to use that graph to figure out when we're going to have a value of only $12,000 left on our car, or half of what we paid. So we paid $24,000. How long does it take to lose half of the value of what we paid for this thing? So like yesterday when we're dealing with real world values, we're only going to graph into the first quadrant because negative money doesn't make sense and negative time doesn't make sense. Okay, the car wasn't worth anything to me before I got it, so we don't want to go back in negative time, and it will never be worth negative money. It'll always at least be worth $0, right? So we're only going to be working in our first quadrant here. We're going to go dollars. I'm going to measure it out in thousands. If I have to get to 24, I'm maybe going to count by 2,000. And then our other axis is going to be time in years. And we're going to make a chart for this. So 0 is always easy to plug in because at time 0 our car had its full value of $24,000. We already plugged in 2 and got 16,934. Feel free to round these off. I mean, you can call that like 17,000 because when you put it into the graph, you know, you're not really going to be able to see a precise value. Since the question asked, when is it going to be worth $12,000, I'm going to keep plugging in values kind of with the goal of finding our answer there with some guess and check. So I'll try 4, and when I plug in 4, I do get right about 12,000. It's kind of a lucky guess. So then we're going to go and plot these points out. So 0, 24,000. 2, 17,000. And 4, 12,000. You could plot a few more points if you wanted to see how the decay curve changes as it gets closer to the x-axis. But we're losing a lot of value really fast in this car. So in just 4 years of owning it, I've lost half of my money on it. This is why anybody who is a financial advisor will tell you that buying a new car is actually the worst thing you can do. Cars are not investments because they lose money very, very quickly. So finding a decent used vehicle that's already lost half its value is the best way to go. Then you don't lose as much of your own money. If you choose to take personal finance next year, we'll talk about that a whole lot more.
You teach personal finance?
I do not, no.
How
I just know what's in the class, but I don't teach it. There's 40,000 homes in your city. Each year, 10% of the homes are expected to disconnect from septic and connect to sewer. Write an exponential decay model for the number of homes that still use the septic system. So to write our model, we're going to use the A, 1 minus R to the T. What's A in this problem? 40,000. What's R? 10%. And T. So we'll clean that up. Make it a 0.9. Still in part A, it says now use that model to estimate after 5 years. So plug in a 5. You get 23,620. That's how many houses will still be on the septic. Second part wants us to graph it and use that graph to find when we're going to have a value of 17,200. So we're going to use some guess and check in the chart to try to find that value while we're creating our graph. So again, it doesn't make sense to talk about negative time or negative houses, so we're only working in our first quadrant. So this is our houses. I'm going to go in thousands again. And this will be our time in years. And if I have to get up to 40,000, I think I'm going to count by 4s. So for our chart, 0, 40,000 is the first value we would use because that's a good, easy thing to plug in. It's just a starting value. We already plugged in 5 and got 23,620. Our goal is to find 17,000. So maybe try 7. And that's 131. Not there yet, so maybe I'll try 9. And they get 15,497, so I passed it by. So it must be about 8 years. You could actually go back and plug in 8 if you wanted to, or you could just know that it must have crossed over the 17,200 between those two values. So we're going to plot it out. 0, 40,000. 5 is right about 24. 7, about 19. And 9, about 15. We're not seeing a really sharp turn on this one because our base is pretty close to 1. Remember, the closer your base is to 1, it's going to be like a straight line. So with a base of 0.9, that's pretty close to 1, and we're not seeing a sharp turn. And then we must have crossed by that goal of 17,000, kind of between maybe around the 8th year. Okay. Questions? This lesson is almost exactly the same as what we've done over the past 2 days looking at 8.1, just the graphs are getting flat instead of getting steep. So 8.2 tonight for homework.